Much of the time spent in Algebra 1 was spent on exploring linear and exponential functions through graphs, tables, and equations. And on the sheet then we gave you graphs at the bottom, tables at the top, and equations in the middle. Okay? So today actually we're going to start Unit 6. Okay? And remember we said Unit 6 will take us up to and including Valentine's Day. Okay? So your test for Unit 6 is on Valentine's Day. Don't be mad at me, Hufflepuff. I love tests. The test is my Valentine.
Because you're teaching it and you just assumed I was upset.
Well, you gave me a look.
You give me a full frame.
I know. Because I'm upset. Okay? Alright? So Valentine's Day is test day. And we're mixing in some ACT stuff throughout there too. So, okay? Alright, so we're going to focus on what's called sequences and series in this chapter 6. Okay? And there's two different kinds of sequences and series that we're going to develop today. And one of them is linear and one of them is exponential. Okay? So that's why we need to go back. We need to think back to our Algebra 1 days. Oops, back is this way. Think back to our Algebra 1 days and figure out how we can look at a table, a chart, and a graph, or a table, an equation, and a graph, and decide if it's linear or if it's exponential. Okay? So, if the function is linear or exponential, find the common difference or ratio on top of it too. So, first table, what are we thinking there in the first table? Linear or exponential? Linear. Why are we going with linear? Okay, linear, and so we're always adding what? Adding 5? Okay, so that constant is the same, so we're looking, so that's linear. Adding, so that would be the difference then. So my common difference is 5. Why is it not getting off of there? Get off of there, get off of there, get off of there. Oh well, I'm over it. Okay? Alright? Okay, so my common difference there is 5. Next one. Is it linear? Why not? If it's linear, then I would be adding the same, right? I'd always be adding 4, right? But I'm not. So right there after the first two, I know it's not linear because that difference is different. Okay? So then I've got to look at something. So maybe it's, oops, I went too far on that one. So maybe it's times 3, times 3, times 3, times 3. So that would be exponential then. And my common ratio would be 3. What I'm multiplying by to get that next term. That's a ratio then. Okay? Number 3. Exponential or linear? What? Neither. Neither. So, if I were going common difference, right, then this would be negative 100. This would be negative 90, right? So is it linear? No. Kick that one out right away. If I'm going common ratio, I would multiply here by 0.9. Right? Okay? 1,000 times 0.9 gets me 900. Right? Well, what's 900 times 0.9? 810? Okay, so that one still holds. What's 810 times 0.9? 729? And I'm guessing then that 729 times 0.9 is 656.1. Okay? So it actually ends up being exponential. With a common ratio of 0.9. Okay? So, here you need one of these. I got it buried. Okay? Last one. What is it? Linear. Okay. And then what would be my common difference? Negative 2,000 because I'm going down. Okay. So, yep. Okay. With me on that, those three. Okay. Now, the next one then is equations. How do I tell if it's a linear equation or if it's an exponential? Well, let's go with the easy one first. How can I tell that it's an exponential equation? What about the exponent? The variable or whatever variable I'm using is up in that exponent spot. So that's exponential. So which one of these or which of these four are exponential? 1 and 4 are exponential because we have a variable up in the exponent. Now, does anybody remember then how to find the common the common ratio then? Here it would be 3/4, so it's the base of that exponent. Yep. So here the common ratio is 3/4. Over here, the common ratio would be 6. Okay. All right. So in that case, it's the base of whatever we're taking wherever the variable is the exponent of. Okay. Linear, thinking y equals mx plus b, or in some cases we're thinking b plus mx, kind of a flippity-floppity it around. Okay, so these two are linear then. And does anybody remember how to get the common difference? It's the number it's attached to again, but this time it's not in the base spot. It's this number, the coefficient. Whoops. It's the coefficient right there. Okay? Whereas over on these it was the base. Okay? Yes. That one would be -3 because it's subtracting 3. Good job. Okay? Out of a graph, how can I tell if it's linear or if it's exponential? Linear is a straight line. Exponential is it's a curve. Okay? It's either going to curve up or it's going to decrease in. So, first one, what are we thinking? Linear. Okay. Second one, what are we thinking? Third one, what are we thinking? I'm thinking it's exponential because it's not quite straight. Okay? So I would think exponential here too. For those of you first time in this room, just so you know, we're still tweaking our new, whatever you want to call this, smart board, smart TV, whatever you want. And so, yeah, it's a work in progress. Okay? And I'm not going to ask you to find those because you got to look at graphs and stuff. But we could estimate here. We could say that this common difference is probably, so we went from 32 to, I would say 36-ish. So I would say somewhere in the neighborhood of 4. Okay, it's an estimate there. Okay. On that next one, I would say that it probably went, I would probably say, because you'd have to go, so it went from 10 to 15. So I would say that that common ratio would be about 1.5. Okay? Because you take in an exponential, remember, you take the next term and divide it by the term right before it to find that common ratio. So 15 divided by 10 is 1.5. Over here, I would say 20,000 to 16,000. I would probably say 3/4. Ish, somewhere in that range. But again, without actual hard data, it's just an estimate. Okay? Now, on that last one, how did I know that it was less than 1? How do we know that this common ratio on that last one is less than 1? Taylor? It's because it's a decreasing. Yep, it's decreasing instead of increasing. Yep. Increasing with exponentials, remember, it has to be bigger than 1, your common ratio. Decreasing has to be less than 1. Okay? All right. There we go. So, new definitions. An arithmetic sequence. Okay? We're going to be talking sequences and series. And the difference between the word sequence and series is simply what you're doing with it. A sequence gives you the list of terms. Okay? That's what a sequence is. A sequence is a list of the terms. If we add them all up, if we find the sum, which we will do next week or the week after, okay, then the sequence becomes a series. Okay? So the series is then when we just add them all up. A sequence is we just write them all out. Okay? All right? So an arithmetic sequence is a sequence of terms in which the difference between any two terms is constant. This would be linear. Okay? Arithmetic sequences are your linear sequences. Geometric sequences are your exponential. I don't like it when it does that. OCD. Oh, and by the way, for those of you that have never had me, I have OCD. Skylar, you know what I mean? Okay? Alright? So, if it's arithmetic, it's linear, we're always adding. Okay? And I use adding loosely because you could be subtracting, but subtracting is just adding the opposite. Okay? Alright? Geometric, you are multiplying. in the arithmetic sequence, we're always adding. What are we adding in that sequence based off of those first 5 terms? We're adding 3. So my common difference there would be 3. Okay. Our arithmetic, we said that one already. It was linear. Okay. What is the common difference related to the identified family? Yeah, exactly. All right, so what are the next 3 terms then? 19, 22, 25. Do we agree? Yep. 19 would come next because 16 plus 3 is 19. 22 would come next because 19 plus 3 is 22. 25 would be the last because if it comes to add. Okay? I'm trying to figure out what I wanted to say there with that last one. Gotta go look, gotta go look, gotta go. Oh, okay. So, the function family, it's linear, right? So then, what do we call that part of the common difference? In a line, it would be the slope of the line. Yep. Okay. Geometric ones we said were exponential. Okay. So in this particular case, what is the common ratio? What am I multiplying by to get the next term? Multiplying by what? Negative half? Are these switching? Because if I multiply positive 1,000 by negative 1/2, I'd get negative 500, right? So just 1/2. Yep, just 1/2 then would be my. Because you were thinking that if we're decreasing, so it's got to be negative. That's in arithmetic cases. Okay? In multiplication cases, it could be negative, okay? But our signs weren't changing. Okay, so then what are the next 3 terms? 125 times 1/2 is 62.5. 62.5 times 1/2 is 31.25. 31.25 times 1/2 is 15.625. Okay. If you wanted to write them in fraction form, that would be fine too. It would be 125 over 2, then it would be 125 over 4, then it would be 125 over 8. All the same. Okay. Finite sequences. Okay. So there's 2 different kinds then. So there are 2 different kinds of sequences in series. Okay. Then there's 2 different kinds of arithmetic sequences in series, and there's 2 different kinds of geometric sequences in series. One is called finite. Okay. Think of the word finite. It means that there's an end, right? Okay. So a finite sequence ends. It stops. It doesn't go on forever. An infinite sequence goes on forever. Okay? And there's one thing that you got to notice is the old ... That's what's going to tell you whether or not it goes on forever. Now, I will tell you this though, that we could write this sequence, 36, 72, comma, whoa, whoa, and whoa. Once again, why is it not? Ay. Come on, computer, catch up. Okay, so where was I? I was on the ... So right here. the dot, dot, dot. So we could write a sequence like this, 36, comma, 72. Oops, that's supposed to be a 72. 72, comma, dot, 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 comma, 288. Okay? That is not an infinite sequence. Okay? We can put the dot, dot, dot in between, and it still is a finite sequence. However, if the dot, dot, dot comes at the very end, and there's nothing else after it, then that's what's saying it's going on forever. Because you might have a sequence that has like 50-some terms in it. Okay? You're not going to write out all 50 terms. Okay? You're going to put the dot, dot, dot there, and then put the very last term. That's still a finite sequence, even though the dot, dot, dot is there. Okay? So, finite sequences come to a stop or an end. Looking at the first one, let's work top to bottom. So 25, 21, 17, 13, 9. Is that a D? D is common difference, R is common ratio. D is adding, R is multiplying. Okay? Is that a D case or an R case? D. And what is D? Negative 4. Okay? So here this one would be D, and it would be negative 4. Okay? In the second one, D or an R case? R, and R would be 2, because I'm doubling it every time. Okay? Infinite sequences. D or R in the first one? D, and D is 5. Second one, D or R? R, and what is R? What? 0.1 or 1/10. Okay? Remember, to find any term, we'll go down here for a second. Okay? In a arithmetic case, D, oops, that's bad D. D is any term minus the term right before it. Okay? That's how you find D. Okay? In geometric, R is any term divided by, oops, I forgot the word term, divided by the term before it. Okay? So D is subtract the term, so you take any term, the term right before it, subtract it. Okay? R, take the term and divide it by the term right before it. Okay? So up here, we could have said here 55 minus 50 is 5. Or we could have done 60 minus 55. 65 minus 60, 70 minus 65. All of those are equal to 5. Okay? And then down here, we could have gone 20 divided by 200. Or we could have gone 2 divided by 20. In both of those cases, those reduce down to 1/10 or 0.1. Okay? Likewise, we could have done 1/5 divided by 2. 1/50th divided by 1/5, and so on and so forth. Okay? All right? Now, there are two different types of formulas that we're going to do here. You have them at the bottom of your page. Just so you know, Mr. Kruger and I decided last week that we are going to focus on the explicit formula. Okay? We're going to focus on the explicit formula because you can get any term whatsoever based off of the explicit formula. Okay? The recursive formula, we're just kind of showing it to you because it might show up on the ACT. Okay? But the recursive formula only gives you the next term. That's all the recursive formula gives you, is that very next term. The explicit formula you can use to get any term. That's why we're focusing in here on the explicit formula. Okay? Recursive only is limited. It only gives you the very next, oops, you guys going this way, the very next term. Okay? That's all that would give you. Or it would give you the term right before it. That's it. Limited. Okay? Explicit, you can find any term of the sequence that you want. Okay? Which is why we're focusing. Okay? Now, we're going to go we're jumping off of the note sheet and we're jumping into your textbook on page 470. Okay? Now we're going to jump into this a little goofy here, okay? Because we're going to jump in on page 470. We're jumping in on problem number 2. We skipped over problem number 1, okay? So it's going to ask us, excuse me, to go back to what we previously did. Ignore that part. Let's just do the math, okay? All right? So consider the sequence in problem number 1, question number 2, part A, number of tiles, okay? Ignore that part too, okay? We're just looking at this. That's where they got this data from, was that question number 1, or problem 1, question 2, part A, blah, blah, blah stuff, okay? So it's looking at the number of tiles, and it's asking us to use the explicit formula to determine the 5th term, okay? All right? Well, we should probably do a little back work on that. So, how many tiles are in the first one? There's 9 tiles here. How many tiles are in the second design? 12 tiles here in the next design. 15 in the fourth design. 18, right? Now, really, to find the 5th one, you would probably just do what? Add 3, right? Okay? Because it's the next one. Okay? But we're going to use that next one because we know it's going to be 18. Or excuse me, we know it's going to be 21. I know that because I'm always adding 3 to get the next design. Okay? And that pattern's going to continue. So I know that that's going to be there. But now I want to show you how we could use the explicit formula to find that because we already know the answer. Okay? So the explicit formula for A, is this arithmetic or is this geometric? This is arithmetic because we're adding. So the explicit formula is A sub n equals A sub 1 plus D times n minus 1. For you, I believe it's right at the top of your page. Okay? It's right at the top of your page. Yep. It's written just like that. Or it's at the bottom of your note sheet from that we started with. Okay? Now, A sub n here is any term that we're looking for. Okay? A sub 1 is the first term. D is our common difference. N is the term number that we're looking for. Okay, so in this particular case, I'm looking for the 5th term. So I am going to find A sub 5. Now, this is not A5, because that means 5 times A. This is A sub 5, which tells me that I'm looking for the 5th term. So we have to write that 5 a little bit smaller and a little bit lower. Okay? Is equal to the 1st term. What was the 1st term in our sequence? 9. Okay? D is our common difference. How much are we going up by every time? 3. N is the term number. It's also right there. Okay? It's this number right there. So N here is going to be 5. Okay? And now you just got to do the math. 5 minus 1 is... Whoa, 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 whoa. A all of a sudden came along for the ride. See, again, I love me some smartboard action. Okay, 5 minus 1 we said was 4. 4 times 3 is 12. 9 plus 12 is 21, which is what we wanted it to be. Okay, so we get what we wanted it to be. Okay, so let's get a little farther now. I want you to use the explicit formula, and I want you to find me the 25th. How did they say it? The 25th term. Okay. So find me the 25th term. You can do it right underneath that one. You can, because we're not going to do question number 3 there, so you can do it right underneath there. Find me the 25th term. Hold on. Not due till next Friday. So 25 minus 1 is 24. 24 times 3 is 72, right? 72 plus 9 is 81. I get 81 blocks to make the 25th term. Agree? Okay. All right. Okay. So we can use that one. Okay. Now we're talking triangles. Okay. So now I think this one's on there too somewhere, isn't it? It's a page back. Wait, hold on. Number 2. Hold on. One more. Yeah. Apparently not. Okay. All right. Fine. It's number 2. What number 2?
On page 470.
It is number 2 on page 470. All right. Yeah. So that's black triangle. You just put it in the wrong spot. That's okay. That's all right. I'm over it. Okay. So we're still on page 470. Okay. So now again, we got to look and see how many black triangles we have. So in the first one, how many black triangles do we have? We have 3. In the second one, we have 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. We're only counting black triangles. 9. Okay? In the next one, we have 27. Because we got 9 up here, and then we got 3 sets of 9, so that's 27. Your eyes are better than mine. I'm going to guess 81. Did you count them all, Taylor? No. Okay, what the pattern? Okay. I'm going to guess that there's 81 there. Okay. Is this a linear pattern?
No.
No. So that means it's a geometric sequence. Okay. So now it says use the explicit formula to determine the fifth term. Well, based off of the pattern, the fifth term should be how many? 243, right? Okay, so we should get 243 over here for the next one because we multiplied by 3 every time. Okay, all right? So now let's use the explicit pattern, or the explicit formula. So this one is a geometric. Now, for geometric, we, instead of writing A, we wrote A for arithmetic. So now instead of writing A, we're going to write G. Okay? So G sub n, the nth term in my sequence, is equal to the first term, G sub 1, times R to the n minus 1 power, where R is my common ratio, n is the term number that I'm looking for. Okay? So in this particular one, G sub n here is going to equal, what's the first term in my sequence? 3. Oops. Times, what's my common ratio? My common ratio is 3. Okay. I'm looking for the fifth term in my sequence, so n is 5 minus 1. And that's in the exponent. Okay. So 5 minus 1 is 4. 3 to the fourth power is 3 times 3 times 3 times 3, which is 9 times 9, which is 81. And 81 times 3 is 243. Don't worry, I am not going to make you find the 25th term in this sequence. Because it would be ginormous. Okay? As Buddy the Elf said, these toilets are ginormous. Okay? Like the movie Elf. Hufflepuff, we're fighting. Did I stutter? Okay. Now we're on the next page. Okay? So what I would like you to do is I would like you to identify each sequence as arithmetic, geometric, or neither. Okay? Neither is if it's not adding by a constant or multiplying by the same number. Okay? And if possible, meaning if it's arithmetic or geometric, find the 50th term in that sequence. Okay? So do A and B and C, please. Okay? A, B, and C. So let's spot check here. First one, part A, type of sequence. I don't have a linear, I have an arithmetic. Why is it arithmetic? Because it's a linear relationship. Okay? Because we're adding 4 every time. Okay? So the type of sequence here, it would be an, whoa. An arithmetic. Okay? And then it's asking us to find the 50th term. Well, that would be a sub 50 is going to equal my first term, so that's negative 5, plus d was 4 times 50 minus 1. Right? 50 minus 1 is 49. 49 times 4 is what? 196? $196 plus negative 5 gives me 191. Okay? This would also be an infinite arithmetic sequence because the dot 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 says it's going on forever. Okay? With me? Good there? Okay. Second one, did anybody get the second one done? It's neither, right? Okay? Because here, if I'm adding, so I could be, this would be like plus 1, but then here it's plus 0. So that immediately kicks out arithmetic. Here, I'm multiplying, I don't even, 0 times anything is 0, so that's definitely not going to work out right there. Or if I go further on down the line, 1 times 1 is times 1, 1 times 2 is times 2, those aren't the same. Okay? So neither, it's not adding by the same number, it's not multiplying by the same number, so this one is a neither case. Get you back over here. And then that means I can't find the 50th term without, actually I do believe, if I'm not mistaken, that's the Fibonacci sequence where you're adding the previous two to get the next one. Okay? So 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, so you're adding the previous two to get the next one. So we could find the 50th term because there's a pattern. It would just force us to figure out the first 49 terms, okay? Which ain't fun. Okay? C, okay? And then, by the way, I changed it to, I should have scrolled down, 13th term instead of the 50th term because it's probably really super teeny tiny. But anyways, okay? So type of sequence. Geometric, okay? Okay, and then define the 13th term. So this would be G sub 13 is going to equal 27 times, what's my common ratio? How do we remember how we found the common ratio? Take any term and divide it by the one right before it. So 9 divided by 27, 3 divided by 9, 1 divided by 3, all of those reduce down to be 1/3. Okay, so this would be 1/3 to the 13 minus 1 power, right? 13 minus 1 is 12. So that's 1/3 to the 12th power times 27. Okay. Actually, let me rewrite 27 as 3 cubed. Okay. So then this becomes, doing some wonderful world of math, 3 cubed times 1 over 3 to the 12th, using my exponent rules, this becomes 1 over 3 to the 9th, which if memory serves me correct, 3 to the 9th is 19,683. Okay? Hufflepuff, I didn't do that in my head, just so you know. I cheated. The blue homework sheet that I handed out to you, that is due next week Friday. But I wouldn't wait until next week Thursday to do it. I would still do it over the weekend while this is still fresh in your minds. Okay? Have yourself a great, grand, and wonderful day.